So my name is Teppo Hemiä. I'm the CEO of Wirepas, and I'm going to discuss about industrial IoT connectivity challenges. First, what are the problems that we are seeing there? Then some of the new ways of tackling those. I will introduce you a decentralized autonomous device connectivity concept, and I will give some examples and cases where we are applying them. And just before, I just very briefly introduce where I'm coming from. So the company is called Wirepas. We do device connectivity, and we especially target for large-scale installations. Established as a spin-off from Tampere University of Technology, 2010. We are headquartered in Finland, offices around the world, and our business model is software only. We license protocol software, and already in relatively short time we have become a market leader in Northern Europe, approaching a couple million metering points in public deals, and we are growing now heavily, and that's why also backed by pan-European investors from Germany, here London and Finland. And I just want to use the opportunity for a timely announcement that we did last week. So we have a brand new board set up, and Andrew Gilbert is now the new chairman, who used to be executive vice president at Qualcomm, and in the executive committee we have Jörgen Lantto, who has some 25 years history at Ericsson, and more recently as a CEO delivered a tremendous growth for fingerprint cards, and Vesa Laisi, who is president at Danfoss, being in power drive business for 15 years. So we are very excited to have the new team members in the board for our next stage and phase of growth. So our mission is really to deliver fit for purpose in terms of connectivity in various segments. And with that mission, we believe that we are getting into and understanding many different problems, and solving those, we are learning fast and enriching the product for the whole ecosystem benefit. This is really our approach. And further, how this works is so that Wirepas connectivity protocol is hardware independent. It can go with any hardware on any frequency band, and that combination together integrated into the smart devices creates autonomous decentralized network. As simple as that. So we are solving a lot of the fragmentation problems in the industry and enabling infrastructure-free networks which are fueled only by the devices themselves. And I will give you more examples later. So we claim that IoT is now the driver for connectivity, and there are several reasons. So if you look at the latest mobility report of Ericsson last November, we can see that the amount of connected devices, when they are attached to humans, they start to saturate in the range of 10 billion points. But when we look at the IoT and they are attached to devices, there's no really upper limit, and it's really exploding. But the volume itself is not the main reason why IoT is really the driver today. It's because within that huge growth, there is a tremendous amount of different use cases who have very different care-abouts of power, latency, throughput, and so on. And that high diversity is a game changer for connectivity, because we cannot anymore look to things in a narrow verticals. It's much wider problem to solve. So the way we model this fit for purpose is the following. First of all, the cost, the overall lifetime cost is very important. It starts from simple planning of the network, simple installation of the network, ability to achieve very high reliability and full autonomy and autonomous operation of the network itself. Really everything that keeps your maintenance cost at a minimum level. Then you need to be able to achieve privacy and security requirements. In some industrial cases, people don't want the data to leave the factory, for example. And the security, there is no final word for it. So you need to provide strong solution for it, but at the same time, it needs to be open and modular for the updates that are coming, whether they are business needs or regulation driven. And that brings to the next bullet, which is the future-proofness, which we are seeing very, very important. And that is the capability and ability to update over the air. Not only the application, but also even the protocol, because the thing that we want to achieve is to maximize the lifetime of the hardware installed. And if they start to be 10 to 20 years, which is very different from the mobile phone business, for example, where the cycles are much faster, you really need to build capabilities to update your hardware. Then on the fourth point is the functional value, and that relates to that diversity. So there's no point of building platform for the sake of platform if it doesn't meet the business needs of given segment. And finally, the business model. There are a lot of services around there that are trying to capture recurrent revenue models in different parts of the ecosystem and different parts of the end-to-end system. But if you stack them all, it may become unsustainable business model for the whole service. And that's why the business model is also a very important factor of the overall fit-for-purpose problem statement. So I will go through a few examples where we are. Let's take first the smart metering, electricity, water, gas metering. A layman may think that these are very similar from the connectivity requirements point of view. In fact, they represent quite extremes. So if we take electricity meter as an example, one of the main care about really is the SLA levels, the reliability that the network can provide. And now the evolution within that segment in the past 2-3 years has been very fast. So the meter is not anymore a meter. It's actually a sensor for the grid. So it's read more and more frequently, and there's more and more data to be read, not only for consumer billing purposes. So that you can have dynamic supply-demand understanding, you can make more accurate investments for your transformers, maybe even in future enable direct trade between producers and consumers. While in water meter, the highest care about is really the autonomy of that meter as it is battery operated. So it's quite different approach. And then in gas metering, on top of that, you need to be able to deliver very fast alarms if there's a case of leakages. When we continue to lighting, we want to support different addressing schemes, broadcasting information to the lights, group casting, unicasting, and then you want to not only control the lights or luminaires, but also different types of sensoring around it. And those two can be very different quality of service requirements. The lighting themselves may need to be in very low latency, only a few milliseconds per hop, while the sensors around in very long autonomy, enabling ultra-low power. And in asset tracking, this is one of my favorite, where you are really pushing a tough combination of requirement because you need to support high in and outflow of assets and keep them connected and enable densities up to 1,000 radios in the cube meter, and I really mean connected, and again achieve a long autonomy. And in quite many applications, we are really looking hard on the range that we can achieve for the connections. But when we are in urban environment, and this is a study done here in UK, where path loss measurements were done in the cities, and we can see that the link budget is not only the answer to build the coverage. In this example, 20 times higher output power gives you only 2 times longer range. And that should give the idea that there must be some better way to reach the coverage. Don't worry, I won't go through this table in detail, but this is one way of summarizing certain use cases, and there's plenty more of the different care-abouts. But this is really the reality of IoT, and not only what they are today, but how they evolve within each. That's really amazing change in the connectivity business. And if you want to look more on that, we did a white paper with Frost and Sullivan that you can download in our website freely and look more in detail some of the use cases discussed in that white paper. So let's then have a look on concept of autonomous decentralized device networks. So here is one illustration of the differences between traditional networks and decentralized one. On the left-hand side, you can see the typical elements of traditional networks, which consist of centralized network management system, whether it's located in the cloud or local server. And then you build different hardware SKUs for different roles in the network, whether they are routers, repeaters, concentrators, and so on. And finally, you have the end node, the sensor or the meter. In decentralized system, actually all of that is within each of the nodes. So key thing is that the decisions are done locally, and the quality of the decisions is way beyond any centralized system. Because now the devices can between themselves, based on the very close by environment, decide which frequency they operate, what time domain they use, and how they build up the routing towards the closest backhaul connectivity. So the principle is that every node is extending the network with its whole range, and the role of router can be taken on the fly depending what's best for the network at that point. Still, just to make no mistake, a router at most power optimized mode in standby can consume less than 20 microamps. And still, depending on the physical layer choice, the distance between the nodes can be several kilometers. So, thanks to that decentralized system, you also simplify the usage of the network by far compared to centralized one. At simplest, you have an API telling send and receive. And that same mechanism can be used across different use cases. And now the trade-offs between power, throughput, latency are done at the protocol level with the given quality of service needs that you want to give per node. And being hardware independent, you can choose the best performing physical layer for that. So the new thinking is to build up the connectivity based on service layers that are giving the services for the upper layers, which is quite common in system development and software development in general. So now we are separating protocol and hardware design in connectivity. And let the both parts unleash their innovation. So as a result, we can map these, of course, in different use cases, but just to give you a couple examples, with decentralized approach, the link budget requirements are fraction from the star topology type of functions, which in some cases give a lot of benefits. Your let's say, building propagations improves dramatically, and not to mention how to get into deep basements in large installations. So to summarize the total cost of ownership benefits, you may save already on the hardware side because you don't need to go for external antennas, you don't need to implement that powerful radios. The infrastructure planning is very minimal as it is not existing apart from the backhaul connectivity. And then more importantly in IoT, where the operative costs are dominating over time, there is a big value for the reliability that this system gives you, having capability to take the connection to any of the neighboring node and improving the node availability. And I can't emphasize more the importance of the over-the-air update. That also is part of the operative cost. And when all this decentralized network itself is running on the non-licensed band and free of operator, it also saves in your data plan cost. So let's take an example. This is one big deployment going on in Oslo, where 700,000 LCD meters are being connected with this approach. And all you need is the meter, nothing else. And that's a quite amazing saving in the total cost of ownership. The connectivity hardware radio itself is open market off-the-shelf sub-gigahertz radio, and 1 out of hundreds is the backhaul connectivity point. But this whole 700,000 is a single network which has multiple gateways, and all is happening in fully automatic manner without any intervention from the backend. And if we apply the business model of one-time royalty fee, we can calculate the data cost over a longer period of time, getting unlimited amount of data for 15 years at less than 2 cents per meter per month. And like given in the example, with this setup, the meter range extending helps on the basement coverage as well. Another example is coming from logistics, where the DACs are installed to the assets, trolleys, pallets, parcels, and in this case, there's a similar use cases as a minimum as in RFID, but you don't need any readers because all the assets are connected. And on top of that, when some of the nodes are given anchor positions, you actually have continuous location information also coming out from the network as a service. And on top of it, the bidirectional communication to the sensors themselves. Again, open market off-the-shelf, silicon can be used, even sharing the application and the protocol on the same microcontroller, and achieving as high densities as 1,000 radios per cube meter. And as a final example, so as a summary, this type of architecture doesn't need control for the network itself. However, you can ask the nodes to deliver the decision data and how they are observing the surrounding radio environment. And with that, you can build very scalable tooling to monitor at any scale of network. And here we have a demonstration ongoing in our booth if you want to have a closer look how it works. So that's concluding my presentation. So we believe that IoT is now driving the connectivity, and really new way of thinking is needed. And the whole market is very diversified, and even the different domains are evolving very quickly. And we believe autonomous decentralized network can be solving many of these problems. And we also emphasize the business model associated with these connectivity systems. So thank you.
Thank you very much.